So welcome back for part 2 of 7.1 notes. Just a reminder that what we're really trying to do here is link the motion of two objects. One is this push pin that is rotating on this cylinder, and the other is this falling mass that is pulling the cylinder via the cord. So last time we looked at the relationship between angular displacement and distance. And so we saw a bunch of things. Let's see what we've got here. Let's say that the push pin started here, and let's say that it just went a quarter of the way around. At this point, you should understand that that change in angle would be pi over 2 radians. All the way around would be 2 pi radians, and this is a quarter of that. Okay. The next thing that you should understand is that if you take the change in angle times the radius, you will get the arc length. And the arc length is this curved distance. It's a portion of the circumference. So in the last video, we saw that the radius here was 0.05 centimeters. So I could calculate this arc length. It would be pi over 2 radians times 0.05 centimeters. And if we were to multiply that out, let's see what we get. We get 0.078 meters. I'm sorry, that's 0.05 meters, not centimeters. It's 5 centimeters, which is 0.05 meters. Okay, so that's 7.8 centimeters. And based on the scale of this picture, hopefully that makes sense. Now, if the cylinder rotated 0.078 meters, then this mass over here should have dropped 0.078. Let me try that again. Again, it should have dropped 0.078 meters. So I'm trying to create this relationship between the circular motion of the cylinder and the linear motion of the dropping object. Okay? And last time we talked about constant velocity, but actually this thing is accelerating. And it turns out that we are going to be able to use all of our same formulas from kinematics. I'm going to add a page. Oh, I have a page added here. I'm going to move it so that I can access it. Okay, so when we were studying kinematics before, we were looking at delta t. We had initial velocity, final velocity, acceleration. Oh, I probably should have started with displacement. My bad. Okay, displacement, which of course comes from initial and final position. And then we have initial velocity, final velocity, and acceleration. So we are going to create rotational analogs. In other words, things that go together here. So in the last section, we saw that linear velocity is equal to angular velocity times the radius. So linear velocity is equal to angular velocity times radius. Okay, so we would say that angular speed, because its direction is always changing. So I'm sorry, I misspoke. So angular speed. And the key between them is the radius. So this is going to work for initial velocity as well. So this would be initial. Okay. How about position? Now, in a circular situation, we're going to be measuring position in terms of angle. And again, we've got this relationship where the linear quantity is going to equal the angular quantity times a radius. In the notes, I wrote it like this initially. This is what you'll see in a math class, that arc length equals angle times radius. In physics, I'm going to write x because we use x to show distance. We could do this for an initial value as well. And actually, the one we're really going to use is this displacement one, the change. So this is angular displacement. Time doesn't need a conversion. Time just works. But acceleration is going to be a little different. The unit or the symbol for angular acceleration is an alpha. So this is a Greek, oops, I should capitalize that. Greek letter alpha. It means angular acceleration. Now this is not the same thing as centripetal acceleration. Centripetal acceleration is due to changing direction. Angular acceleration is due to changing speed. A rotating object that is speeding up will have both. The relationship between linear acceleration and angular acceleration then, again, will be the radius. All of these quantities on the left here, sometimes, depending on the textbook or who's talking, you might hear linear acceleration or you might hear the word tangential. And the reason that you might hear that is that the motion of an object at any given instant, the motion of an object going in a circular path at any given instant is tangential to that circle. So the velocity at any given instant is tangential. Okay. So once we have all of those correspondences, we can take our kinematic equations and adjust them. Okay, so I'm going to write down our kinematic equations from before. It's a good review. And basically, all of the same math applies because the velocity is still the change in position over the change in time. Acceleration is still change in velocity over change in time. So what I'm going to do is I'm going to translate these by making the appropriate substitution. So for example, instead of delta x in the first equation, I would plug in angular displacement, which is delta theta. So I would, instead of writing delta x, I would write delta theta equals 1/2. And then instead of writing v, or v naught, I'm going to write omega naught, and then plus omega, and then times delta t. So let me continue that process down here. That's what I would be looking at. I've been doing this for a while, so I have these memorized. You might want to write them on a card so that you can make those correspondences. Again, t is the only one that's the same. so there are my four kinematic equations for linear situations and then for rotating situations. Okay, so let's see. I have written them here as well. And also just a reminder of how these things are related back to the definitions, that the definition of acceleration was delta v over delta t, and now angular acceleration is change in angular speed over delta t. And just again, also a reminder that the link is the radius. So let's try some practice problems. We've got 3 more to go here. Number 1, Earth has an average daily distance from the sun of approximately 1.5 times 10 to the 8th kilometers. Find the average daily distance traveled. Okay, so we go 1/360th of the entire way around, right? So the circumference of the Earth's orbit would be 2 pi r. It'd be 2 times pi times 1.5 times 10 to the 8th. So that's 942 million, or about 9.42 times 10 to the 8th. Oh my goodness. Kilometers. Okay, so let's just try to picture this a little bit. So what we're talking about here is there's the sun, and there's the Earth, third planet out. We've got this orbit, and that's the distance all the way around. In a day, though, we only go 1/365th of that. So our arc length is going to be the circumference divided by 365 to just how far we would just go in one day. So I'm going to take that number and divide by 365, and we get 2.5 million, about 2.6 times 10 to the 6th kilometers. So the next time somebody asks what you did today, you say, well, I went about 2.6 million kilometers. Okay, next part. Find the average daily angular displacement. Now the angular displacement would be how big this angle is. How big of an angle do we sweep out in a day? So all the way around, the angular displacement for the entire thing would be 2 pi radians. But for one day, it's going to be 2 pi divided by 365. And let's see what that is as a decimal. It's going to be pretty small. 0.017. That's not terribly big. A radian, by the way, let's see, we know that pi radians equals 180 degrees. So if I wanted to figure out how many degrees there were in 1 radian, I would divide both sides by pi. So 1 radian is about 57 degrees, just to give you a sense of that. 0.017 radians is pretty small. Okay, find the angular acceleration. Okay, well, in order to have angular acceleration, we would have to be speeding up or slowing down. And the Earth's orbit does not speed up or slow down tremendously. It actually does a little bit because technically it's elliptical, but it's essentially zero. Essentially, we're moving at a constant speed. Okay, let's try another one. A top spinning at 15 revolutions per second spins for 55 seconds before coming to a stop. What is the average angular acceleration of the top while it is slowing down? Okay, So first of all, this 15 revolutions per second, that is an initial velocity, but it's not given in radians. We would like it to be in radians. So what I'm going to do is change it into radians. There are 2 pi radians in 1 revolution. So this would be 30 pi radians per second. It's coming to a stop, so the final velocity is 0. The time is 55 seconds, and we want the angular acceleration, so we want alpha. So now this process is just like we did before. We would go back to our equations and pick one, and it's this one that I want, the one in the middle of the page. So final velocity equals final speed equals initial speed plus acceleration times time. So 0 equals 30 pi plus alpha times 55. So alpha would equal negative 30 pi over 55. You could reduce that, negative 6 pi over 11, or you could change it to a decimal if you wish. I actually like to leave it in terms of pi because it's just one less step for me. Okay, draw an angular speed versus time graph for the situation. Ooh, so when we studied kinematics, we made a lot of graphs. We made velocity versus time graphs. Let's try it here. Let's see, let's go 0, 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60. Okay, there's time in seconds. On the other axis, I'm going to put angular speed. We started at 30 pi, and we ended at 0. So it would look something like that. Yeah, and then the slope of that line is the angular acceleration. That's pretty cool. Also, the area, if we wanted to find it, would be the delta theta, or the number of radians swept out by that top, which is another thing we could compute. In fact, we could compute that with this formula. And check it out. This formula is essentially the formula for a triangle, which is what this is. We've got the base. The base is delta t. We've got the height. That's our initial speed. And the final speed is 0, so 1/2 base times height. Pretty cool. Okay, one more example. A roll of newsprint accelerates from rest. Okay, that's our initial angular speed. With an angular acceleration of 15 radians per second. Okay, angular acceleration is alpha, 15 radians per second squared for 180 seconds, delta t. Find the angle swept out in this time. Okay, so here we go. Delta theta equals speed times time plus 1/2 alpha t squared. So this is 0 plus 1/2 times 15 times 180 squared. Okay. I get 243,000 radians. Now that's a lot. That's a lot. If you wanted to find out how many revolutions that was, if I divide by 2 pi, I'll see how many turns that is. 38,674 revolutions. That's quite a few turns. If the radius of the roll is 10 centimeters, find the distance traveled by a point on the outside of the roll in this time. Okay, so what's cool about this is to find that distance. Oop, I'm in math mode. I'll go to physics mode. To find that distance traveled, I'm going to take the change in angle times the radius. I already have the change in angle, 243,000 radians. And then remember that the radius is 10 centimeters or 0.10 meters per radian. So radians actually cancels and I get an answer in meters. And it'd be 24,300 meters. All right. Thanks for watching, and